Okay, thank you very much again for attending. Let us begin. For today, actually, the discussion is a bit shorter on, or rather, we're just gonna wrap up the last two instructions, or rather, three instructions about the single cycle processor. Specifically, what we'll do is we'll do branching and jumping. So this completes the entire story, at least for the basic instructions that we can do. With the instructions presented last week, all the load word, store word, arithmetic operations with immediate, and then if you add branching and jumping at the same time, we already have a processor that can do even simple, complex, or well, ironically, complex operations like matrix addition, subtraction, things like that. Okay. But of course, this is just a bare bones single cycle processor. But I'd like to emphasize that the only thing that you have to take in here is the philosophy or the strategies that we're doing in order to understand, okay, how are processors made? Because when you're maybe in the near future, when you take a digital design job, you will be able to use the same ideas. Okay, it may not be exactly RISC-V, it can be other processors, but you'll be able to take similar or same ideas into account when you design. We'll discuss something similar by the end of this lecture. But for now, we'll focus again on branching and jump instructions. All right. So for branch instructions, recall that if we call BEQ or BNE, branch if equal or branch if not equal, we compare two registers, x1 and x2, and then we jump to some address offset L1. So actually, the way I wrote it is branch to PC address L1 if x1 and x2 are equal. The more appropriate, really, term, I guess, I should have written this better, is branch to PC address, we'll put that word here, offset L1. Meaning, for example, you have this set of instructions, right? This is 0, 1, 2, 3, whatever this is. Okay. And then the third is a branching instruction. It's a BEQ. But I want it to jump to branch 1. So essentially what you're going to do is that you're going to branch offset. You're not going to specify that you're going to branch to address 1, but rather you're going to specify, hey, how much jumping should I do? If I want to go back to 1, I have to specify that branch offset as -2 because I want it to jump to 1. So it's like 3 minus 2, you get to 1. Okay, so that's the more appropriate way of thinking of branching rather than you're targeting the exact PC address. Because the way it's said in the spec sheet is that, hey, I'm going to branch to this PC plus that address offset, whatever that is. All right. That also goes the same for jumping, right? So it's more appropriate to say it's a branch to PC address offset rather than the exact PC address, right? But the idea is very simple. You just have to compare registers x1 and x2, and if they are equal, you jump to that target offset. Let's say I want to jump um, 12. If I started from 3 and I want to jump to sometime that address below, if I'm gonna jump 12 steps downward or 12 next steps, that's essentially pointing to PC address 15. Okay, so it's something like that. It's pretty much straightforward. All right. So again, it's very simple because if you try to look into the instruction format specified by the RISC architecture, all you have to do is just get the entire branch instruction type, branch instruction format. Um, Understand that, hey, this is how my immediates are arranged. Okay. Now, if you remember from last time, I did mention that we have sort of four types of immediate instructions. We have the normal immediate, we have the store immediate, branch immediate, and then we also have the jump immediate. Okay. For the branch type immediate, it looks something like this. I have no idea why they made it this way, but I think it was meant for purposes to ensure that RS1 and RS2, the func and the opcodes are the same for other instructions with like R type and I type as well. All right. But for now, let's accept that these are the rules or the specifications that are given to us. Now, slicing this is very pretty much straightforward because all you have to do is literally slice those instructions again. But you have to, again, take note of how to rearrange the entire immediate instruction. All right. Now, it's just a matter about filling up the decimal form, convert it to its binary form, and then if you know how the images are arranged, you can write your I could name this as my B type immediate as just a concatenation of the specific slices. All right. Now there's a note here that you see a magical missing bit zero. Well, I wouldn't call it missing bit, but a bit zero is appended at the end. Because if you look at the B type instruction, the the lowest immediate is until 4:1 only. And then it's automatically assumed, even if you check the spec sheet, that it's 1 prime B zero. Now we'll get back to that in a bit after figuring out, okay, what is the data path or the data flow for my branch instruction. Again, the most important thing when you call the branch instruction is that, hey, I'm comparing two registers, x1 and x2. That already gives you insight into, okay, how do I access these register sources, right? That's why it's specified here that you have RS1 and RS2, okay? And then I'm going to have to immediate offset, all right, the offset L1 depending on how you specified it into the branching, okay? So if I'm going to look at my branching instruction and I'm going to check out, hey, how am I going to uh, plan out my data path? It's very simple again. So let's start off with, hey, I picked up my program counter. I loaded the instruction. And the first thing I'm going to do again is to decode the instruction. Remember, I needed RS1 and RS2. So it's loaded here in addresses 1 and 2. Not a problem. And then I also have my immediate extended. Not a problem too. Right. So what about the control signals? The question again is, am I going to write into a register? No. So you have to set it to 1 prime B 0. So this becomes 0. Why don't we write to any register? Because we're not literally writing anything to a register. So we don't have to mind it. But we have to make sure that it's 0 so that we don't overwrite any specified address here in A3. Okay, so you have to make sure that's 0. ALU source is 1 prime B0. Why? Because we're going to compare x1 and x2. So the ALU will grab RD1 and it's going to grab RD2. Right. So the ALU source over here, which is this blue line over here. So we're going to set to 0 because we're going to have to get RD2. Okay. Let me erase this a bit. No, I'm going to erase this too. Anyway, it's clear. Right? And then ALU operation. So when we compare operations, right, we compare them by setting the ALU operation to subtraction. All right. And then you know if it's equal or not if the 0 bit or all the bits of the result is 0 or are 0 rather. All right. Say for example, source A is I don't know, 10 in hex. So you could write with the 0000 something up to A, the 32 bits. And then source B is also 00 dot 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 A. If you subtract them both, you will eventually get an A result that is 0. Or if you remember, like last time, one of the specifications that was mentioned in the ALU is that a 0 bit must occur if all the bits of the ALU result is 0, right? And then that 0 bit is sent back to the control unit. Okay? So the reason why we use subtraction is, okay, to compare, hey, am I a 0 or not? If one of them, or if the result is neither positive or either positive or negative, as long as it's not 0, then the 0 bit will never be 0. Okay? So that's the control signal that tells us, hey, my branch is taken or not. So if the branch instruction that I'm looking at is branch if equal to, branch if equivalent, right? That's what BEQ is. Then I have to check if it's 0. But if it's BNE, branch if not equivalent, I have to check if my branch is not a 0. Okay, and that will trigger us to tell, hey, I have to jump to the address offset L1 rather than not take it. Okay, so I think it's pretty much straightforward. We discussed this in the instruction lecture last time, so review that a bit if you need help. Okay, so I hope it's clear that we use the sub subtraction operation for that. Now, what else is important? Memory write. Are we writing to memory? No, so we keep it at 0. Oops, I forgot to write. The ALU operation should be 001. Are we writing to memory? No. Are we? Does the result source matter that we're feeding back into the register? Actually, it should be a don't care, but for safety reasons, let's just write 0. All right. It can be a don't care, not a problem. Oh, not this one, but this one rather. Okay. Not a problem. What about the immediate source? We have to use the B type format. So down here in the immediate source, the one that's controlling your immediate extension is 10. Okay. And then for branch if equal to, if 0 is asserted, all right, as especially for the equivalent version like we've discussed earlier, if 0 is asserted, meaning source A and source B are equal since we subtracted them, then we have to update our program counter over here using the PC target, which is as you can see here, it's the PC source plus the sign extended immediate extension, the appropriate one, plus the target is equal to the target. And then that's what you're going to feed back into the PC source, right? But you can control your PC source using this PC source control signal, the one that's controlling this multiplexer over here. All right. So if we're analyzing BEQ and it's a 0, okay, or the 0 is asserted, meaning they are equal, it satisfies the branch, we have to take the branch. Meaning we have to select 1, right? This control signal here needs to be 1 if branch is taken. So that the next PC update will be the PC target that we're trying to get. Otherwise, if branch is not taken, because the 0 signal is not asserted, because source A and source B are not equal, then it has to use what? PC plus 4, right? So you have to set it to 0 if it's not taken. So that the next PC address, it will take this path over here. It's very simple, right? So all of these are happening again in one cycle. That's why it's a single cycle processor. So the only important things you have to take note of is that it's pretty straightforward to set which registers that you have to use into the ALU. But the additional step that you have to consider is, hey, what is my 0 vector? Or sorry, not 0 vector, but what is my 0 signal? If the branch is taken, I use the PC target. If it's not taken, I have to use PC plus 4. It's that simple. Okay. So again, what's the key thing to remember here? All you have to do is just to remember, okay, which sources are important, which signals are important, how do I control them, and how do I set the control signals appropriately. All right, it's that simple. So that's for branch equal to extraction. Okay. Uh, Again, just to remind you guys, the table for immediate types. So for the B type immediate, it's different from all other types. You can just use this. Okay, you can set whatever wire you have to prepare this set of immediate format. Okay, so it's for the branching. So just a hint, I prepared this already for you. It's a matter of you just sort of copying it on me. Okay, but I don't know how you plan to do it, but this is some sort of a hint of at least how I did it. Okay, so that's for the branch immediate types. What else? So here's another thing that to consider that I mentioned last week that our program counter only takes in uh, or rather it updates using the PC plus 4 path, which is this one, right? So you have to adjust your program counter. You can put it outside or inside the program counter. It's entirely up to you, but I prefer that you put it inside because you want to modularize your work such that, hey, I want to make this module as your program counter. But it's entirely up to you. Okay, I'm not stopping you from where you want to put this additional feature where you take in a signed immediate. Okay, you shift it and then you add it to the main program counter. Okay. Now, there's a tiny detail that you have to consider. If you read the PC specs, uh, according to the RISC-V instruction set, when you do a sign extension, you have to shift it once. Actually, shift once only. So shift to the left actually. Shift left once. I forgot to write that down. You have to shift it to the left once. It's an SL1. It's mandatory. I have no idea why, but I think it has something to do with allowing you to make sure that every uh, every offset that you're doing is always a multiple of 4. Okay, I'm gonna explain a bit, but the only thing you have to remember is that when you take your sign extended, so this one, the moment you take this value, you have to shift it to the left once. Okay, before you start adding it to the program counter, this path, and then putting it into the multiplexer. So if I'm gonna go back to my to our single cycle, we have this extra shift actually here. You have this shift left one. Okay. So you have to add it there before you add it to the program counter. Okay. And then you're gonna put it here. But according to some books, they already put it in here the moment you try to select that. Okay. So for now, we'll stick to what the RISC-V tells us to do because that's the standard that they're asking. Yes, Tim, you're asking? You're raising your hand?
Sir, kapag sa instructions, 'di ba yung offset doon is like in terms parang in terms of force na siya, sir. Multiples of 4 na siya.
Yeah, okay. That's a good question. That's for store word. Okay. So in the store word part, okay, that's a very good question. Say, I'll try to clarify that. Array. I don't have a clean register. Sorry, I don't have a. Oh, nice. Okay, so just to give you an idea, right? That's a good question. In terms of multiples of 4 for store word instructions, we already assume that. But when you do branching or jumping, it has to follow this format. It's not you sort of put in actually I don't know really understand why RISC-V wanted to do it in first base. I may have to read up on that. But the thing is that if you do it for branching and jump instructions, it's not always in multiples of 4. Why? Because the one who's doing the job of setting the load immediate is not or rather is according to the compiler already. Because the way we code these things, right? If you remember, hey, I have my instructions. I want to branch and equal to register 1, register 2, and then I specify the branching target. We put in a name in the branching target, right? But what we do really is that we don't put in the exact immediate jump, right? Or the exact offset that we're putting, right? We're specifying the name. And the one who's handling the specification for the actual immediate value is not us, but rather the assembler and the linker who's doing that. Now, apparently, it's the linker or the assembler because they have this algorithm inside already that, okay, I know I have to jump to this instruction. Let's say, for example, the loop says I'm going to do an add I next, right? Okay. And I don't, let's say it's in step number 52. Okay. So it's the link or the assembler who's gonna append that 50. What it's gonna do is that I'm gonna calculate, hey, I'm at address, let's say 40, right? And then the loop is at address 52. What the linker is gonna do is that, okay, I'm gonna calculate this and I'm gonna put that there. Okay. But we're not doing that. So we don't really specify the immediate, right? But the one that you're pertaining to is that unlike for storeward instructions, right? SW X0, you specify the immediate, right? 12, and then X0 something 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 or whatever register that you're trying to put in here. So this, yes, it is in multiples of 4. Or rather, it's in the software's designer's perspective that, okay, I have to put it in multiples of 4. Now, in some cases, it may not be in multiples of 4 because of you have actually instructions that are load half words, right? But in our case, we assume right now that they are in multiples of 4. Okay. So, quick answer to your question. For store words, yes, we do that. But for branching and jumping, we specify the loopers or something, or the not the loopers, but the labels. But it's the linker or the assembler who does that. Okay. And apparently, because since it's the linker or the assembler who's doing that, we sort of need to understand in the lower level that, hey, they're doing this requirement that I specify any immediate, okay, but I have to shift it once to the left pa, because that's what the RISC-V tells us, that if I do branching or jump instructions, I have to do this mandatory step before you add it. Okay,
Okay, sir.
long
So,
story, but I hope it makes sense. Yes.
sir, on top of the magical zero, mag-shift left once pa.
Yes, correct. So on
Okay,
top,
sir.
very, very good, very observant. You're very observant. On top of this magical zero, you have to shift left one more. Okay. Now, there's an advantage to that. Actually, gonna put it here. Okay, pinangunahan mo yung slides, but that's good. All right. But on top of that magical zero, right? Because you're always dropping zero, that value, whatever this value is always an even number. Okay. And then you have to shift it because it's an even number, right? And then you shift it to the left once. Okay. That's effectively trying to multiply by 2, right? That ensures you are always within multiples of 4 bytes, right? I guess that's the reason why they made it this way. Like for example, right? For example, 0101 is 5 in decimal. If you drop that bit, because you're just grabbing the lower part, right? If I drop that bit, because you're taking that out, you get 0100. That's technically 4, but you shift it to the left once. You shift it to the left by 1. So that 0100, if you shift to the left once, that's equal to 100. That's still 8, which is a multiple of 4, right? Let's look at another example. Let's try 30011, right? I drop the MSB, I get 0010. That's actually equal to 2. I shift it to the left once, I get 0100. I am guaranteed that I'm always multiples of 4, right? So, uh, okay, I think this also sort of goes in line with your question earlier that, um, yes, since we're accessing, yeah, okay, let me add a little bit more information to what you asked earlier. Since we're accessing the instruction memory, and we cannot really access like half of an instruction memory, right? It's always in multiples of 4 because again, we have to grab the entire word, right? The way the RISC-V instruction set was built with this and with that specification that you have to multiply it by 2 later on ensures us that we're always getting multiples of 4 bytes. So we're always guaranteed to get a word that it's not half of it, but always getting a word. Okay? Does that make sense?
Opo, sir. Opo. Thank you, sir.
Okay. Okay, good, good. Very good of you to be very attentive, observant about it. And actually, I'm not the maker of RISC-V, but I believe this is the reason why they did it this way. Okay, since we're accessing the instruction memory in terms of bytes, words rather, so it's always guaranteed that we always have to make sure we're accessing in multiples of 4. And since they made it this way, right, we're always accessing multiples of 4. I think that's the entire gist of it. Okay? Okay, that's a very good question. I hope that's clear. We can repeat the video again just in case. But bottom line, always make sure to include this shift left once. So actually, the biggest hint already here is that if you make your program counter module this way, you're good to go. Okay, you're good to go. This drawing itself is already fixed for you. And if you do it this way, it's done. You're totally done with it. Okay. What else? Okay, a little bit more on the branch instructions. There's another hint actually. I'm sort of giving out a lot of things that you could consider in your design, but really setting the PC source is that if my opcode is a branch, if my PC source can be a 1 or 0 depending on these two conditions. One, if the opcode is specifying a branch if equal to, and I get a 0 value from the ALU source, ALU result rather, then PC source is 1. Otherwise, if my PC source is getting branch if not equal to, and then I get a not a 0, I set PC source to 1 to get the branch taken path. Okay? Now, don't don't forget to make sure that no write back to register nor memory is asserted because we don't care about that. Steps for memory access and write back are not important because immediately after executing the subtraction in the ALU, you just have to specify if you're gonna take the branch or not. So change the PC source or not. That's it. Okay. Any questions in the branch? I hope, man, it's also clear for you. If you have questions later, we can discuss them. Okay. What else? The next part really is jump instructions. It's the same thing. Okay. It's the same thing as branch. The only thing in jump instructions, especially we're using JAL, rather. Okay. The reason why I specified JAL only for now because I want to make sure you guys understand rather than having to do too many instructions in our design. I want you guys to uh, take more time to appreciate on what you're trying to design rather than to bombard you with so many instructions to process, right? Now, like jump instructions are like branch, except we don't consider the zero signal from the ALU. Instead, what happens is that we immediately jump to the target destination register. Okay. And the other thing is that we have to save the current PC plus 4 data into the destination register. Now, that's something that I won't spoil right now. I want you guys to think about on how am I going to add that, right? Not in here. Oh, yo. Okay. Hold on. Wait. Hold on. Okay, sorry, I'm back. Okay, so the jump and link instruction allows us to the nice thing about jump and link compared to branch sometimes because some software engineers can actually do jump and link instructions without using a jump and link instruction, but rather using branch and not equal to or branch instructions, and then you mix with other add I or other instructions. But in RISC-V, we have a special jump and link instruction, which allows us to jump to an extended 21 bits immediate wide. Because branch instructions only use, it's here. If you count this thing, it's like around 20, 21 plus 6, 20. Okay. You have to add how many bits that is. So there's a trade-off in terms of how many maximum bits you can jump into. Okay. So actually, no, not including this, just this. So 7 plus 6 plus 11, 10, 9, 8. So it's like 13 bits wide. So the resolution of jumping that you do with the branch is not that high. But for jump and link instructions, since it's 21 bits immediate, you can jump even farther. Okay. Now the JAL format is also a messy one, because but it supports a 20-bit immediate, right? Well, technically 21 bits immediate because it's 21 bits wide, but you're only grabbing 20 bits immediate. And if you notice again over here, okay, it stops at 1, so you have that lower 1 prime B0 again. Okay. So for jumping, it's pretty much the same as branching, except you jump immediately without having to consider the comparison made in the ALU. All right. So no need. It's immediately a jump. But you have to take note that when you do a JAL, right? A JAL, let's say X1, and then the immediate, okay, or the whatever label immediate you have. Okay. So you have to store the current PC plus 4 into the X1 register or whatever register you specify. You have that extra step. Now I'm not gonna spoil that in here. I want you guys to figure that out. Well, actually, it's very easy to do, but It's part of the exercise. Okay, but maybe we'll add a little bit of details about jumping into the. Oh no, actually, I did spoil it here, right? So, aha, something's not right in my drawing. Okay, so let's try to go through the steps again, right? So you have the jump instructions. Again, we're gonna program counter, decode the jump instruction, we specify the address that we want to write into, okay? But this time, the reg enable is asserted. Why? Because we're gonna write into a specific address, right? ALU source, we don't care about the result of the ALU, really, because the one that's computing the target address is not the ALU result, but rather you have this dedicated PC target that's used inside your program counter, right? And then the ALU operation, you don't care because you're already using this addition inside the program counter. Now, ALU result is quite tricky because actually this is wrong. This path is wrong. It's not supposed to be here. I'm sorry about that. I will use a different color. Ink color. I'll use blue. You have to connect this. It's not that you don't store, or sorry, rather, the one that you're storing uh, uh, in the register is the current program counter. So it's supposed to be this one. Okay, this is coming from the current program counter, this blue line. You get that, grab that, and then up connect that here, going here. Okay, so your ALU, your mem to reg will not be 1 bit anymore like this one. You have to make it 2 bits wide because the 00 will take the one that's coming from the ALU result, but you don't need that. The 01 comes from the memory, but you don't need that either. What you need is 10. The path that you take is the one which is the output of the program counter, right? So that's the one that you have to send back into the register. Okay, because that's the one that you need for the JAL instruction. JAL X1 and then the loop offset or whatever that label is. Okay, I'll keep using loop because that's the one you usually use, right? But the one that's stored in here is not the next target address. Again, it's not the next target address. Okay, it's not that. It's the current program counter, right? So it's gonna store that into the register, right? That path over there. Now here's the thing. Again, the IM source, you have to use the I type. Okay, so that's 1 1 over here, down here. Sorry, not I type, but the J type immediate. And then your PC source should grab the one that's not the PC plus 4 path, but it should grab the one that's in the PC target path. Okay, so you have to set it to 1 because you have to jump immediately to the next target. So that in the next clock cycle, it's already using the new PC plus target address. Okay, dokie. Very simple, right? So jump, pretty much the same, but you have this extra path here. Okay, you have the extra path to consider. Okay, and again, you're storing the current PC counter, not the new PC target, right? And this here becomes an additional 2 bits. Why? That's why in your homework, actually, Mads, the one you're asking earlier, in your homework, the reason why I specified that mem to reg is 2 bits wide is to accommodate the jump instruction, which a while ago you were saying or you're already getting into. Okay, but just to make it sure it's clear, the one that you have to get again, I will repeat. So I know I'm being repetitive, but repetition sort of helps with memory. But the one that you have to get is the program current program counter, not the next program target address. Okay. So that's for the jump instruction. All right. Time check. Okay, we're about to finish. Okay. Actually, that's the gist of it. That actually ends our single cycle story. All right. So last week we had operations, the memory operations, arithmetic operations, and memory operations. Today we discussed both branching and jumping, and you have to modify the PC component a bit, and then make sure to add the necessary changes to the controller and program counter modules. Okay. So I hope it's clear. Yeah, I hope it's very clear. If you have questions, we can go back to it. Now, here's a very, very quick discussion about single cycle. Actually, do people still use single cycle processors? You will rarely find commercially available single cycle processors. Why? Because you see, the recent processors or the ones that are commercially available are all in pipelines. Why? Because single cycle processors have very bad latency. It's like horrible latency. I'm gonna make it red again just to overemphasize that. Where is my pen? Ink color red. Okay, it's a very bad latency, so bad that your processors are operating very, very slow. However, some special single cycle processors are still useful for low power and variation resistant applications. Okay, but we won't discuss it today. If you're interested, we can discuss it next time. But what we want to do is that we want to relate it to our performance metric from last time. Okay, so say for example, I have the same single cycle processor, but I am given the what they call this the delays for each component. For example, the register clock to queue. If you remember all your registers, the moment the clock kicks in, the edge of the clock, the output of the register changes after, it updates the output of the register after the clock edge. So that's the reg clock to queue, right? So it's like from here to there. That's the reg clock to queue. Register setup is the time it takes for your data, okay, to be updated in the next clock cycle, because you need to make sure that, hey, I need enough time for my data to be settled first before I start clocking in the next edge. Okay. And all of these are logic delays. If I have some logic here, like the ALU, right? If this the guy over here, the ALU is like what, around 120 picoseconds. That. Actually, I think it should have been nanoseconds. But anyway, doesn't matter. Okay, these are all the delays. Now the question really is that what is the fastest allowable clock frequency? Now from your older courses, oops, I think this has to go first. Okay, from your older courses, recall that we measure the fastest allowable clock based on the register to register path. And the shortest period is the allowable time needed to settle all digital signals, right? Because everything that you do in digital design is that we do things by transferring logic from register to register. That's why we call them RTL, register transfer logic, right? So I have a data here, I update the data. Once the data is updated, okay, it goes to some logic, and then eventually it's updated here, but it has to settle before the setup time of the next register, before the next clock cycle, right? So if I'm gonna draw the period, right? So within one period, from clock to you to the logic plus the setup time for the next register, everything should be there. Okay. Now that was taught to you in your previous courses. Now I won't. If you need time to talk about that again later, we can discuss it. But I won't go it step by step right now because it was taught to you before. But the point is that the the period that you have to work out is the sum of all those things: clock to queue, the logic plus the setup time. Okay. So with all of these things here, okay, you're gonna have to add everything. And now here's the thing. The delay depends on every instruction. And the longest instruction is actually the load word. Why? Because the load word, okay, so the PC here is a register. You have to take the clock to key of the PC. All instruction memory reads are combinational. All in register reads are combinational. You have to go to the ALU. You have to go through, well, you could, you have to go to the memory. And then you have to go to this multiplexer. And then you have to go to the setup time here. Okay, so you have to add all of those things. So you could imagine this is a combinational logic. So clock to queue is what? Like 14 picoseconds. That's this one. And then the instruction memory is, what's the memory? Like 200 over here. Register file, if you look it up here, is RF read. Okay, it's 100. And then the ALU is 120. The memory is another 200. All multiplexers, where did I put that here? Is 30. Okay, and then you have the setup, which is 60. So you have to add all of those things, and that will be your minimum clock period. So if I put it down here, right? Oh, sorry, I wrote that here. Again, clock to queue, register clock to queue, this one. this one, this one, this one, this one, this one, and then the set of time over here. Okay, you have to add all of those things. If you add all of those, what do you get? You have around 700 picoseconds. Okay, and if you that's the minimum period from register to register, because the register to register path that you have is the this register, and then all of this. It's like one whole big chunk of combinational block, and then this is your next register again, right? So it's like from going out here, and then eventually your output of your combinational block will get back to the register here, right? And you have to satisfy 750 picoseconds minimum. If you calculate that in frequency, okay, uh, oops, I didn't calculate whatever frequency it is, but if you remember, our CPU time is given by the number of instructions times the period of a single cycle, right? And let's say we're gonna run, and the minimum clock cycle is the worst case because this is the worst case, right? Regardless if you do store word, register, even though you only need less time, but the worst case needs to be satisfied because you're using only a single clock, right? So this 750 picoseconds is the minimum clock period that you're gonna need. And if you're going to run 100 billion instructions for some program, how long is the execution time? That's around 75 seconds. Sure, 100 billion instructions is like so much, but you know, what if we can go actually even faster, right? What if there's a way to do it faster? Oh, there, I computed it. So 750 picoseconds is actually 1.33 gigahertz. Okay. That's not even close to how AMD or Intel processors use as 2.5 gigahertz as the minimum, right? So the problem with single cycle really is that we are limited by the longest instruction. This one, right? It's so bad that your performance is, you know, we're not even twice or even as good as Intel or AMD processors for that matter. And what more if you're gonna have to do complicated uh, logic too? Okay. Now here's the thing: what if we can cut the logic into parts, and what if we can reuse some components? And that's what we'll explore next week. Multi-cycle paths. Okay. Now we won't be designing multi-cycle paths, but one thing I want you guys to realize for next week is okay, for multi-cycle paths, um, it's a design philosophy, right? That hey, I can actually cut my logic into parts, right? And there are clever things that you could do, such that you could multiplex and you could quote unquote pipeline things. But for next week, we're gonna multi-cycle stuff, and you'll see the benefits of it. In terms of performance, there may not be good performance. It depends, right? So we're gonna check that out next week. So again, summary for single cycle is that today we've taken up branch and modify jump instructions. You have to make sure that the necessary changes are done for the controller and program counter. And then a side note that single cycle is rare nowadays because it's just too slow. Okay, but there's some benefits for it. Okay. So yeah, that's pretty much it for hold on, time check. We have 10 minutes more. That's pretty much it for the discussion, but you're feel free to stay for a bonus content, which is tips for machine exercise. Since there's just a few right now, I don't mind, but I'd like you to embrace a few design philosophies. You see, uh, for me, digital design is a very much favorite topic because it's like art for me. It's like painting, right? You sculpt your work based on the specs that are needed. It's so nice because all you have to do, hey, I have specs like this, and then it's up to me how I want to make it, right? Now, the thing is that good digital designers look at architectures first before designing. And you gain more experience in digital design the more you look into different architectures. Okay? Just like painting, right? Good painters know how to paint really well or sketch because they look at several designs or paintings, right? Therefore, analysis is usually done first before designing. And that's what we're trying to do. When I was teaching you about single cycle processors, I was trying to lay out the foundations and the analysis. Okay, how do you make single cycle processors? Once you're used to it, you can design your own single cycle processor and maybe make an even better architecture, right? So here's the thing. It's usually easier to visualize what you want to do when you have a drawing, right? I've emphasized that even from last week over and over again. Hey, look at it, right? That's why we have a top-down approach, is because I wanted you to look at the bigger picture first, and then you look into the small details. That's how artists do it too, right? They learn by looking at drawings. They look at the bigger picture, they are amazed by it, and then they look into the tiny details. That's how digital designers also do it. You learn by looking at architectures. Now, one key lesson from CoE 111 is or actually from your CoE 111 or any similar subject, is the concept of register transfer level. That's the minute details that we have to look into. If artists, painters, practice yung strokes, right? The strokes that they do, the color gradients and stuff like that. Us digital designers, we practice the concept of register transfer level, because you always have to frame your thinking of how data flows. And from the name itself, it's always from register to register. A register will be updated. That's my current data. I want to transform it through some combinational logic, and I want to save that data in a new register. That's why it's called register transfer level. Okay, and the nice thing about it is that makes your uh, it makes it easier for modular design, right? So because you don't have to think of too many things, you think of it step by step. If artists draw a Mona Lisa, right? Leonardo da Vinci drew Mona Lisa. He was very particular about the strokes that he was using. Us as digital designers, we are particular about, hey, how do I want to transfer data from register to register, right? And if you frame your work that way, it's so easy to design any digital circuit. Okay. So the reason why I'm telling you this is because in most cases, how we treat our classes is very theoretical, right? Now, here I am trying to make you realize the theory, how theory is actually done in practice. Okay? And the reason why we're trying, it's called this way, art, like RTL. Okay? So what I wanted you to do, review the videos back again, and what I want you to do is that observe how data is transferred from register to register. For example, data from the program counter, right? It spits out an address, and then combinationally it gives me an instruction which I want to save, or I want it to decode into the next register here in the register file. Right? Again, R, transfer logic, R again. Now data from register, there's another path, data from the register file to the data memory. Right? Well, the data memory is technically a memory, but you could think of it like a register. Okay? Because registers are memory elements, right? So register, transfer logic, register again, right? And you don't have to think about too many things at once. You can just think about, hey, if I want to get data from my register file and put it into data memory, what do I put it to? What do I want to put into my data memory? Look, these are just the combinational logic that you need, right? Maybe a multiplexer and then an ALU. Do I have to mind all the other things? No. I can focus on designing these things only. Another one, register file to register file. That could be register file. I'm going to do this. I'm going to add this logic over here, and then back to the register file. Not a problem. Again, it's all about framing the design as an RTL. See, that's the reason why it was taught to you that way. Okay, but very few times we are reminded of it because I don't know, maybe because we're very too much into the theory part. So here's a good example, right? For every module, actually, in good practice, when you start taking a job as a digital designer, every module you do, you always find a code block for registers and combinational logic. And the reason why I wanted you to use System Verilog is because they always have this always underscore FF and always underscore com block. Now it's just a naming scheme, but every digital design, every module that you make, every code, you always find those things because it's a register, transfer logic, and then back to a register, right? Now that's one good example. And if you decide, although it's not really necessary, or it's like an unspoken rule or a convention. It's a common you see the reason why it's because it's a common pitfall to code system verilog as if you're coding in C or Python, because that's how we were told to do programs, very sequential, right? But remember, system verilog or verilog are hardware description languages. Our goal is to design by describing hardware. Okay, we are describing our art, our design. Okay, that's why you have these things. So the key takeaways really for my tips in your project is always frame your design in RTL, and there is always a register and combinational logic block in a module. Okay, look, maybe not necessarily needed right now in order to pass the course, but I'd like to encourage you and look into different architectural designs because they are so cool, right? Like for example, have you ever seen what a multiplier looks like? You know, there are sequential and fully combination of multipliers. That's so cool. They're very, very nice architectures that they have out there. Pipeline architectures are fantastic too. Multi-cycle, yes. And what about CISC architectures? You know, this complex instruction sets, very, very nice too. So they have other versions too, like SIMD, single input, multiple input, multiple data architectures, so much more. And they're very, very interesting to design. Now, a nice research actually. Um, maybe well in the future is to design machine learning architectures, right? So that's something to look into as well. Okay. I have nothing else. Time check. I have 4 more minutes because actually the other thing that I want to share really is okay my own architectural design, right? So the nice maybe something to help you when you design your work is to actually run the elaborated design. Okay. Um, you set your risk score as the top, right? You right click, then there's set a stop button there. Okay. If you set it as stop and you want to see how your uh, design is actually built, you can run this RTL analysis, open elaborated design. Okay. Run an elaborated design rather. And if you do that, you see, okay, how did you actually draw your system? Right? Although you can't really have the full control, like, hey, I want to move it there or here. you know, but it gives you a good idea as how organized is your design. And a good design is something that's quite clear to you. Like for example, see, I have my program counter, right? I have the clocks and resets going into my system. Okay, my program counter, the address output goes into multiplexer, and you can see some things like register to register, register transfer logic to register um, paths as well. All right. So the reason why I'm mentioning this is for practical purposes. Sometimes you'd like to look at your design. You know, when you're drawing Mona Lisa. Okay, you build this thing, you draw it, and then you look at the bigger picture. What else can I adjust? Right, and then you draw the other parts, and then you look at the bigger picture. Okay, what do I have to connect? Right. So that's how we actually do it. You know, it's like the practical aspect of appreciating your work as well. Okay. So yeah, pretty much it. So it's a tip also to help you guys what you can do, right? And then another thing, maybe last is there's this concept called code quality. So if you notice how I write my code in here, um, I have this OCD of putting them aligned together, right? Because it's so easy to understand afterwards. And I make it a habit to put the begin end instructions, things like that, so forth. So I'm also giving you sort of a few hints on how to design things. Look at my program counter. Very much similar. And then my ALU. Nah, I'm not gonna show that. Okay. Yeah, that's pretty much it. Let's go back. Any questions? 1 hour. Yes, we're done in like less than an hour. Sayang. I'm not gonna show everything. No. Uh, for me, actually, yeah, I could show you a few things, but no, I don't want to show it to you. Never mind. I take it back because it's very important for me that the reason why I put less instructions on like other exams before is I'd like you to appreciate the process of doing digital design, right? That's more practical for me than having to make sure, hey, I always meet the specs and I mean, you're gonna meet the specs and all, but it's really more important that you have that experience, right? I mean, I'm trying to transform all my classes into a bit more experiential rather than um, very theoretical. I mean, I think for your case, Tim, you've experienced that in 197 also, right? I make you do a lot of work because I want you to experience it rather than, and then put in the theoretical part alongside it. You see, because that's the seat of all this, that's what I want you guys to learn, read. Okay? Any other questions? Mads, you have questions? Tim? No questions? Okay, very good. Thank you for attending, and I'll see you next week for multicycle. Right. So I did not upload multicycle slides yet because we won't have multicycle exercises anymore. But I mean, theoretical, yes, but design wise, not anymore. Let's focus on single cycle. Then we'll jump to pipeline afterwards. Okay. We'll stop recording and